Yesterday we have just started with the mechanical properties of solids beta. Introduction we have been completed. Let us try to practice some numericals based upon this topic, that is about your Young's modulus, bulk modulus, and as well as of your rigidity modulus. See this question beta. We have got two equal and opposite forces, each of magnitude capital F, which has been applied along the rod of a transverse sectional area capital A. Okay, we have got what type of area beta? Transverse sectional area. The normal stress to the section of PQ, see the figure beta, inclined theta to the transverse section is equals to how much? Can anyone try it out beta, you see? Make an FBD, we'll get an idea for that one. We are applying the forces on opposite direction right now. Two equal and opposite forces are acting, each of magnitude of your how much for me? Capital F. Let me check it out with this one. Okay. Along the rod of a transverse cross-sectional area capital A. And see, this is a transverse cross-section. This is your area. Now see here, if I'm dropping a perpendicular somewhere right now here, like this, isn't it? This is making an angle theta, isn't it? So P to Q, if I'm making an FBD, just make an FBD of this one better. FBD of P to Q. Okay, so this is the cross section what we have taken. Okay, on in this point, if I'm applying the forces, see how the force has been applied. One force is in this direction, capital F, and area of cross section, another force is in the opposite direction. That means if I complete this triangle right now here, so this is your triangular cross section. Okay, now with respect to this one, it is making an angle because this is theta, so obviously this one is also your theta. So along the tangential, there is one force which has been acting right now. That force is nothing but equal to how much for me? If I resolve it, this is your F cos theta. Okay, so area is right now for me this one. This is your area of this one. So this is your actual area. This is your actual area, capital A. Okay, so this one is P, this one is your Q, and this one is, say for example, some O. So if I extend this one right now, if this is theta, this one is also your theta here. Clear beta? Is the resolution clear beta? P2O is right now for me what? Area. So cross-sectional area of P2O is how much beta? So I'm writing here, see, cross-sectional area. Cross-sectional area of PO is equal to how much for me? Capital A. The same way, if I am taking the cross-sectional area of your PQ, just resolve it beta. So PQ will be equal to how much for me? PO divided by cos theta, isn't it? See from the figure, if I'm writing cos theta will be equal to your PO divided by PQ. So cross-sectional area of PQ will be equal to how much for me? PO divided by your cos. P2O is what for me? A. So it is A by cos theta. Clear beta? What is asking the problem? Normal stress. Normal means what's perpendicular. So if I'm writing the normal stress right now for this one, see how do you write this condition? Stress is equals to normal force divided by area. Normal force is nothing but for me how much beta? F into your cos theta divided by area of cross section. That is nothing but if you're how much for me? A by your A cos theta. Just now we got it out. So that will be equal to your F divided by your A into your, this will become how much for me beta? F cos theta divided by your A. So it is nothing but if your F by your A I have taken here right now. So this one I have taken extra A here right now. So I need to remove this extra A because it is A cos theta. Na? So that is the reason. So it will become for me cos into cos. That will become for me cos square theta. So I can write here stress will be equal to your F into your cos square theta divided by your A. So that will be the stress. Clear beta? Is this question clear for you? Is this question clear beta? Clear? So what will be the answer for this one? Fourth option I can write the answer. So I can take your fourth option. Very good model beta. You need to practice such type of your models. We need to be getting such type of your questions in this one. You should make very clear in your trigonometry and application of your terminology which is being used in the question. Okay. Chalo. Let us try to go for next question. This is also a good question, beta. A vertical hanging bar of length L and mass M per unit length carries a load of mass capital M at lower end, and its upper end is being clamped to a rigid support. The tensile stress at a distance x from the support is how much? Okay. Now what is asking right now for your tensile stress? Tensile stress is nothing but again same beta, tension at a given point divided by your area, nothing difference with that one. So I'll just make a diagram for that one beta. We have got a vertical hanging bar of length L and mass M per unit length. That means the rod which is been hanging is also having the mass. So here this is your rod like this. Okay. So mass of this one is right now how much for me? Mass per unit length is given for me. That means lambda. Mass per unit length. Mass per unit length means lambda. Lambda is equals to your M by your L. Done, beta. Okay. Now to this one, there is a block which has been attached somewhere here. Right? This is say for example capital M. This one is smaller. Okay. Upper end has been clamped to a rigid support. Option here, and then very good. The tensile stress, what is exactly is happening? The tensile stress is a distance of your x from the support. That means from the support, we need to calculate somewhere here. This point is say for example x. At this point, I need the tensile stress. Okay, so let me write first the formula. Tensile stress is equals to your tension at point, in whatever the point you are talking, divided by your area. This is our basic formula, beta, isn't it? So tensile stress is equal to tension by your area. Now tension at a distance of your x would be how much, beta? The amount of the force which has been acting on that one, isn't it? That means mass per unit length of the rod into length of this rod, beta, isn't it? So total mass is how much for me? L. So remaining length will be equal to how much for me, beta? L minus of your x, isn't it? So tension at this point is because of what? This lower mass, this lower mass. So this length will be equal to your L minus of your x. Done, beta. So tension at your x will be equal to your M into your L minus of your x into G plus capital M into G. That's it. So I can write here tensile stress is equals to, this will become for me M into your L minus x plus capital M into G divided by area of cross section, that is your A. So first option will be the answer for this. Clear, beta? Is it clear for everyone? Is it clear? Any doubt in this one? Sure. Next one. A wire of length 5 meter is being twisted by an angle of your 30 degrees at the free end. If the radius of the wire is 1 mm, the shearing strain will be equal to your how much? Shearing strain formula. Tan of your phi is equals to your how much, beta? Tan phi is equals to your x by your L, isn't it? So it's asking us the value of your phi. A wire, this is your wire of length 5 meter. This length is 5 meter, very long wire, 5 meter. Twisted through an angle, that means this is your process. It is being twisted by your small angle, that means it will come somewhere here. It is making an angle of your theta at the free end. If the radius of the wire is, given as of your 1 mm, shearing strain will be equal to your how much? Now see here, as angle is very small, so phi will be equal to your x. X will represent me the arc length, beta. X is equals to your arc length. So arc length will be equal to how much, beta? R into angle made by that one. How much angle it is making right now for that one? Say for example some theta. So it is R into your theta divided by your L. Shearing strain will be equal to your how much for me? Angle made by that one is nothing but this one. So R into your phi divided by your L. So theta is your what? What is your theta, beta? So theta is here right now for me. Angle of your twist. Okay. And phi is your angle of your strain. Done, beta? So phi will be equal to your radius is 1 mm. So 1 into 10 power minus 3. It is twisted by an angle of 30 degrees divided by your 5. Okay, so that will be equal to your how much for me? As angle is very small part of relation, 30 degrees you can write in terms of your radians, isn't it? So 30 degrees is equals to how many radians, beta? So it is 360 degrees is equals to 2 pi radians. Then 30 degrees will be equal to your how many radians? Can anyone tell me? Munas Fatima voice is breaking. Okay. So how do you write beta? 360 degrees is 2 pi radians. 30 degrees will be equal to how much? Anyone? 5 by 6. Very good. 30 degrees will be equal to your 5 by 6. Done. So that is 10 power minus 3 into your pi divided by 6 into your 5. You simplify it, you will get the answer for this one. I am leaving the calculation for you. You should be getting the third or second option as of your answer. Sure, next. This one is also one of the very important model beta. One end of a uniform wire of length L and weight W has been attached rigidly to a point in roof, and a weight W1 is suspended from the lower end. If capital A is area of cross section of the wire, the stress in the wire at a height of 3L by 4 from its lower end will be equal to how much? Let me draw the diagram. One end of the uniform wire of length L and weight W is attached to it. So we have got a rod right now here. To this one, a weight is being attached somewhere. This one is W. One end of a uniform wire. Okay, this wire is of length L and weight is for this one. Okay, is attached rigidly to a point in the roof and a weight W1. So this one is W1 is suspended from the lower end. If A is the area of cross section of the wire, the stress in the wire at a distance of 3L by 4 from the lower end. That means from the lower end, somewhere at a distance of, I'll try to write with other pen, somewhere here at a distance of your 3L by 4. What is asking is stress is equals to your how much? Okay, so stress formula is already known for me. Stress is equals to your tension divided by area at that point. So what will be the tension beta right now here? So stress will be equal to, so tension is because of 3L by 4. So weight will also be how much? 3L by 4. That means 3W divided by 4 plus W1 divided by area. Okay, mass is directly proportional to the length. As the length is increasing, isn't it? So lambda is equals to your M by L na beta. So M is equals to lambda into L. So whatever is the length, for that one mass will be directly proportional. So that is the reason for 3L by 4, the length will be 3W by 4. And along with this one, this weight W1 is also acting. So total tension at this point will be because of your 3L by 4 plus the weight of the body divided by area. That will give me the answer. Got it, beta? So what answer I can write? W1 plus 3W by 4 divided by area. Clear? Any doubt in this one? Sure. Next one. What is called the ratio of breaking stress and working stress? This is also a good question, beta. What is called the ratio of your breaking stress and as well as of your working stress? Elastic fatigue, elastic after effect, yield point, and factor of safety. I have not told you this one, but just right now here, right now condition, breaking stress divided by your working stress. By your working stress is equals to your N. N is known as of your factor of safety. Factor of safety. Okay. So what will be the answer beta for that one? So it is called as of your, sir, 11th is hey, yeah, 12th. This one is 11th class ka hai beta. Factor of safety. Done beta? Sure. Next one. This concept I also have not told. So I'll try to do this all concepts right now. Just give me a time. So there was some of the models which I was given for me. So I'll just try to do some of the good models. Then we'll try to continue with your yesterday's session of your class beta. We'll try to continue with your yesterday session of a class beta, wherever you have been stop it. So yesterday we have been just started with your, we have completed what part? Poisson's ratio part has been completed. Okay, let me just. So we just started with the applications. So let me take the next application beta. Applications. Next one. We know that stress is directly proportional to strain beta. Stress is directly proportional to the strain. Stress is directly proportional to the strain. That means if I draw a graph between stress and strain, this is your stress and this one is your strain. It will be a straight line passing from the origin. So that will give me the slope theta. So this theta is known as of your slope. This slope is nothing but tan theta. This tan theta is equals to E. This E is known as of your modulus of elasticity. So stress is directly proportional to strain will always gives me what beta? Modulus of elasticity. That means E is equals to your stress divided by your strain. So we'll be getting the question something like this, like I may be giving you the graph something like this. This is your y-axis, this is your x-axis. On y-axis, if I take stress, on an x-axis, we take if your strain. And the graph is something like this. This is point A, this is your point B. This angle is making an angle of 30 degrees and this one is making an angle of 60 degrees. So what is an Young's modulus of, what is Young's modulus of B divided by Young's modulus of your A is equals to how much? Okay, that means E is nothing but what Young's modulus only, na? That means YB divided by your YA will be equal to your tan of your theta B divided by your tan of your theta A, isn't it? So stress by your strain, YB by your YA, isn't it? For B, what is an angle beta? For B, what is an angle? 30 degrees. So this will be your tan 30 divided by your tan 60. Done beta? Or else if he is asking YA divided by YB, you can write this one as of your tan 60 divided by tan 30. I hope you know this trigonometric values. You can simplify and get the answer for that one. Very good beta. Exactly. Isn't it? YB by YA or YA by your YB, anything depending upon the option what is asking us this. Clear beta? Young's modulus is directly proportional to your stress by your strain. Chalo, next application. Series and parallel combination beta. Series and parallel combination of wires. Okay, so let us try to talk about your series and your parallel combination of your wires. So first one is series. Like see, we've got two rods. This is your first rod. And there is another rod which has been connected to this one. Somewhere here, right? And to this one, there is a block which has been attached, having a weight, some mass, whatever it may be, capital M or small m, depending upon the situation. This is the first length beta L1. This is the length L2. This is having an Young's modulus Y1. This is having an Young's modulus of your Y2. This is having area of cross section of your A1, and this is having area of cross section of your A2. They are one above the other beta. So it is forming what for me? A series combination. So I can make this one as one effective rod. One effective rod like this. Okay. So this is your block of weight capital F. Clear beta? So this total length is L1 plus L2. So what is an Young's modulus in the series combination part? Okay. Now see. When you're attaching this weight beta, this weight is exerting the force on the first wire, then that wire is exerting the force on the second wire. So forces acting on this wire will be equal to how much for me beta? So force acting on the first wire and force acting on the second wire will be one and the same. So I can take in this one, F is equals to force acting on the first wire will be equal to force acting on the second wire. Clear? And what is the total elongation beta? Can you tell me what will be the total elongation in this one? What is the total elongation? As the wires are different, total elongation. So E will be equal to E1 plus E2. Why E1 plus E2? Because their areas are different. So elongations will also be obviously different. And you know how to write the elongation formula beta? We know the formula Y is equals to F into L divided by A into your E. So E is equals to F into your L divided by Y into your A. This is your elongation formula. So this is your E. So it is your F into your length will be L1 plus L2 divided by Young's modulus will be Y in series into effective area will be equal to your A. Clear beta? Is it clear? Okay. Now in this one, whatever the area of cross section I'm taking, area of cross section of this wire will be the same. That means A1 is equals to A2 will be equal to your A. Okay. In the parallel combination, sorry, in the series combination, areas will be the same. That means I can write here force is same F into length is L1 divided by A into your Y1 plus of your F into your L2 divided by A into your Y2. This A will get cancelled right now here. This F and this F will also will get cancelled. So this one is L1 plus L2 divided by Y in series will be equal to your L1 by your Y1 plus of your L2 divided by Y2. Okay. So if I take an LCM, Y in your S will be equal to your, this will become for me L1 plus of your L2 into your Y1 into Y2 divided by your Y1 into your L2 plus Y2 into your L1. So this will be the Young's modulus in your series combination. Clear beta? So tell me why I have taken the area of cross section to be the same, because on both the wires the load is same. So whatever is the change in area in the first wire, the second wire is also having the same change in the area, isn't it? Because force applied on that body is same. If the forces would have been different, then the area of cross sections would also have been different there. But as the force applied is same, so whatever is then extension, because they are made up of two different materials, beta, isn't it? So as the force is same, so area of cross section must also be the same. So in the given situation, I'm taking that A1 and A2 be equal to your same. Now if you tell me what will happen if the length will also same, I can take even that case here, right? If length are same, if L1 is equals to L2 is equals to your L, then Young's modulus in the series combination will become how much beta? Anyone? You see here, L1 plus L2 if they are same, it will become for me 2 into Y1. So here LL gets cancelled. So everywhere L gets cancelled right now, because here 2L, here L will become common. 2Y1, Y2 divided by Y1 plus Y2. Okay. So this will become for me 2 times of Y1, Y2 divided by Y1 plus Y2. Or else this one is 2 divided by your Y in series will be equal to your 1 by Y1 plus 1 by Y2. You can simplify it. So this is like an harmonic mean of, it is like an harmonic mean of your Y1, Y2. Okay, the same way, in case of two springs, also we write what beta? 1 by K will be equal to 1 by K1 plus 1 by K2 in series combination. Okay, so in series combination, this wire is exactly equal to your 1 by K1 plus 1 by K2 part affiliation. Is that clear? So in series combination, effective Young's modulus is being calculated with the formula y is equals to your 2 times of y1 y2 divided by y1 plus y2. So it is an harmonic mean of your y1 into your y2 part affiliation. Now if I'm going for your parallel combination, now tell me what happens. Number 2, parallel. Simple application. So this one is your rod here right now. There is one rod in the direction. And there is another rod now right now. Here, once one rod. There is a wire which is being attached to this one beta. So there is a rod or the wire which is being attached to this one. The weight is being attached to this one somewhere here. This is of your mass of your M. Okay, so this length will be same, this length will be the same, but area of cross sections will be the different. Materials are also will be your different in this one. So force will be also be different. Here some force is acting because here the force will be F is equals to M into G. So on this one the force acting is, say for example F1, and here the force will be equal to your F2. Clear beta? Okay, so in this one the thing what you need to remember is elongation will be the same. Elongation will be the same because we are applying the same amount of your force on this one, isn't it? So elongation will be E is equals to your E1 is equals to your E2. Okay, okay, but force will be different beta. Force will be equal to your summation of both of them, F1 plus of your F2. Like this, if I'm rearranging it into a one single wire, this will become something like this. So this will become for me a thick wire here, and here we are attaching a weight of the body. So this area is right now for me how much? Area of this one, whatever you are taking, this one is your A1 plus of your A2. Length of this one is nothing but equal to your L, and Young's modulus of this one is Y in the parallel if I'm taking right now. Is that clear? Isn't it? So this is the weight of the body M. So weight of the body is M into G in the downward direction. So if I'm writing the force formula beta, F is equals to your, it will be Y in your parallel, area of cross section is A1 plus A2 into elongation E divided by your L. The same way F1 will be equal to how much beta? Y1 into A1 into your elongation E divided by your L. I hope you got that formula. Y is equals to your F into L divided by A into your elongation. Now, so F is equals to how much for me? Y A into E divided by your L. Okay, so from that one I'm writing this one. The same way F2 if I'm writing beta, value of your F2 will be equal to Y2 A2, elongation is same, divided by length will be also be the same. Okay, so if I compare with this relation right now, so as F in parallel is equals to your F1 plus of your F2, so Y in parallel A1 plus A2 into your elongation E divided by your L is equals to your Y1 A1 into E divided by your L plus Y2 A2 into your E divided by your L. This will gets cancelled. Elongation will get cancelled. So Y in your parallel will be equal to your Y1 A1 plus of your Y2 A2 divided by your A1 plus of your A2. So this is your Young's modulus of the wire in the parallel combination. Okay. If A1 and A2 are same beta, if A1 is equals to A2 is equals to your A, then Young's modulus in your parallel combination will become how much for me? Y1 plus of your Y2 divided by 2. Isn't it? So it is Y1 plus Y2 by your 2. So this will be what beta? Arithmetic mean of your Y1 and Y2. Clear for everyone? Clear for everyone? Isn't it? Very important relation beta. In the, if I'm talking about in terms of your springs, in case of your springs, if I'm writing, in case of springs, In case of your springs, K effective in parallel will be equal to your K1 plus of your K2. K1 plus of your K2, where K is nothing but what, beta? Spring constant. K is nothing but what for me? Spring constant of the spring. That means you are comparing the steel wire with your spring. That's it. Clear? Is that clear? See, if you see this equation very carefully, I can write the value of that K. F is equals to Hooke's law is what, beta? K into your X. X is nothing but extension only, no? So it is K into E. Now in the place of E, what I am writing, you see there, beta? E will be equal to, sorry, in the place of your, this one. In the place of your K, K is your spring constant, no? So K will be equal to YA divided by L. If I'm comparing the steel wire with your spring, then the K value can be written as Y into your A divided by your L. Clear, beta? So next one. And very important, next application. So we got a series and parallel combination. The next one is important one, beta. Elongation of the wire, beta. Elongation in the wire due to its own weight, or when you apply certain external force. There are something applications like that we'll try to analyze here right now. So next side heading is elongation in suspended wire due to its own weight. Due to its own weight. Due to its own weight. So we are talking about your elongation in suspended wire due to its own weight. Okay, that means we have got a wire. We got a wire which is being suspended and it is elongating on its own part. So this is your wire. Okay, we've got a wire here right now. Okay, and it is elongating on its own wire. Because of its own weight, it is elongating. Like say here, if I'm taking some weight of this body, isn't it? Say this one is of your mass and the length from the lower end is X. Total length of this wire is equals to, say for example, L. Okay. So this is made up of a material of your Y. Okay. Density of this material is also equal to your D. And mass of this wire will be equal to your how much? Mass I can write in terms of volume into density. Mass is equals to your volume into your density of the wire. Volume is equals to area into length into your density. That is your M. If I'm talking about this small element, beta, this is your dm now. So dm will be equal to how much, beta? Cut at mass by original mass is equals to cut at length divided by original length, isn't it? So cut at mass will be equal to your m into cut at length is your x divided by your l. So force acting on this element will be equal to how much? F is equals to your, if I'm writing the value of your force, F is equals to your m into your g. That is nothing but a dm into your g. Clear, beta? So dm will be equal to how much, beta? M into g into your x divided by your l. So this is the force acting on this. Okay, and this force is nothing but what? For the small element. Okay, just write the data, you'll get confused otherwise. Initially, L is equals to your, if I'm taking as of your initial length, L is your initial length and D is equals to your density of material of your wire. Material of your wire. Y is your Young's modulus. Y is your Young's modulus. So mass will be equal to volume into your density. Volume is equals to area into L into your density. Okay, and what is A beta here? A is equals to your area of your cross section. Area of your cross section. If I'm talking about elongation due to its own weight, what is the formula beta? F is equals to, what is the formula I can write here? Just now written, F is equals to Y A E divided by L. If I'm writing the elongation for this one, for this dm, for dm, elongation will be de, isn't it? So how much amount of force I'm applying on that one beta? Small amount of a force that I'm representing it by letter F. So now if I'm writing de, that is de is equals to your, so what I can write here beta? De is equals to, if I'm taking out de is equals to, that will become for me F into your L divided by Y into your A, isn't it? F into your L, F into your L divided by Y into your E. So DE is equals to F value, how much we got beta? Mg into your X divided by your L into your DL. This L is nothing but equal to how much for me beta? X only, na? Because we're talking for the small element. So it is your dx divided by your Young's modulus into your E. So now integrating on both these sides. Integrating on both sides. That is integral of your dE is equals to integral of your mg into your x into your dx divided by your L into Young's modulus into your into your area. Sorry, why I have written this A? This one is your area A. Okay, so in this one now mass is constant, G is constant, divided by L is constant, Y is constant, A is constant. This is integral of your x into your dx. From what limit? 0 to your L. So that is equals to your mg divided by L into Y into your A into integral of x into dx is nothing but how much for me? X square divided by 2. Limits are 0 to your L. So that will become for me your mg into your upper limit minus lower limit. So it is L square divided by L into Y into your A. This L, this square will get cancelled. So it is mg into your L divided by Y into your A. How much? 2 times. No? So 2 is also there. This is 2 and this is 2. So it is mg into L divided by 2 into your A. That means elongation of the wire, whatever I'm getting is E is equals to your mg into your L divided by 2 times of your A into Y. This is the elongation of the wire on its own weight standard formula, isn't it? So as mass is equals to volume into density, volume is equals to area into length into density. Therefore, if I still simplify it, elongation is A into L into D into your L divided by 2 into A into Y. This A will get cancelled. So it is your L square into density D divided by 2 into your Y. Okay. So G is also there. No? So it is into G because in the upper form there is a G. So elongation formula is L square density into G divided by 2 times of Young's modulus. So elongation of the wire and its own weight in terms of density if is asking, I can use the formula E is equals to L square into D into G divided by 2 into your Y. So overall, this derivation is not that much important for your knee. The only thing you need to remember is the heading, the elongation and suspending of the wire due to its own weight. If I am talking, there is no external weight acting on that body. So in that time, you need to directly remember the formula, because if you sit in your examination hall and go on sit the derivation, you will be literally wasting of your time. So I do personally request that you try to remember. You try to remember the basic heading of this one and directly formula. Elongation due to its own weight is E is equals to L square D into G divided by 2Y. In terms of mass, if I am writing E is equals to mg into L divided by 2 into A into Y, the students will get confused to which formula to be used. It depends upon the data. If mass is being given for you and he's asking the elongation, then directly you can use the above formula. If length is given and density is given, then you can use the below formula. That is very important to remember these two formulas for your competitive examination. Now, something which I am writing right now is really very important for competitive examinations. You generally get the questions on this type of your thing, and students generally overconfidently overlook this one. See the diagram what I am drawing here. Previously, there was only the wire. Now, if I am taking a wire for this one, and along with this one wire, if I am even attaching certain weight of the body, okay, that is mass of your M. The length of this wire is, say for example, of your L, density is your D, and acceleration due to gravity is anyhow small g, and Young's modulus is y. What will be the net elongation, beta? Question is, what is net elongation? What is your net elongation? What is your net elongation? Net elongation is nothing but beta E is equals to elongation due to your force in the wire plus elongation due to its own weight. Okay, so that means E is equals to elongation due to the applied force means F into your L divided by your A into your Y plus elongation due to its own weight means L square D into G divided by 2 into your Y. So this will give me the answer. Clear? So this is your elongation formula. E is equals to your, from this one, elongation E is equals to F into your L divided by Y into your A. So this is your elongation formula. So this elongation plus elongation due to its own weight, that you both of them you need to add it. Then only you'll get the answer for that first type of your questions. Clear, beta? Is that clear? Any doubt in this one? Sure, next one. Next reading. Comparison of wire with spring. Comparison of your wire with your spring. I already written the formulas, but just for your recap, I'm trying to draw it. If I'm taking the such situation, there is a spring here right now. This spring is connected to a block of mass of capital M. So spring force here is F is equals to K into your X. Okay, X is nothing but what? X is equals to E. That is nothing but what? Elongation. Or you can say that is also your compression or extension. Anything you can call that one. Change in dimension. Okay. So if I'm increasing the wire from 0 to your X, then energy in the spring is half into K into your X square. This we did in the work power energy. If I'm increasing the wire from X1 to your X2, energy is given by the formula U is equals to half into K into your X2 square minus of your X1 square. Okay. The same thing I'm right now comparing it with your wire. For your wire, same situation. We have got a wire right now here. This is your wire instead of spring, and to this one we are applying certain weight, isn't it? That weight is nothing but what for me? Force. This weight is nothing but what for me? Force. That is nothing but equal to what? M into your G. This is the wire of length L, Young's modulus L, elongation in this one is E. So that force will be equal to how much, beta? Y is equals to F is equals to YA into your elongation divided by your L, isn't it? So I hope you are getting confused in this one. I'm writing L and X in the same condition. So yeah, force F is equals to Y into your area of cross section A into your elongation E divided by length L. Okay, so here the value of what I'm writing this one, this YA by your L. Okay, so this is your equation 1 and this is your equation 2. So if I'm comparing 1 and 2, comparing 1 and 2, so we are getting K is equals to how much for a minute? YA divided by L. So this is the spring constant of your wire. That means equivalent spring constant will be equal to YA divided by your L. That means energy in this one I can write as, I'm using the same formula, U is equals to your half into K into X square. I'm writing the answer smartly instead of doing the derivation. So energy I can write it as this energy. I got the value of K. So energy formula I'm using this one. U is equals to half, K value is equals to YA divided by your L into your extension, that is nothing but E square. So this is your energy stored in the wire. So this is your what? Energy stored in wire. Energy stored in the wire is calculated by this formula. You can even rearrange this one. U is equals to your half into Y into A into E divided by L into your E. Okay, so this can also written as U is equals to half into, this will become for me F into E. So energy in terms of force, because this value is nothing but what, beta? Force only, na? So this energy is called as what? Strain energy. Strain energy. So energy stored in the wire is given by the formula U is equals to half into F into your E. Okay, if there is an extension from E1 to E2 for a given wire, if extension is from E1 to E2, then how do you write the energy? Same like previous one. U is equals to half into Y into A divided by length L into your E2 square minus E1 square. So that will be the energy. Very simple application. Okay. If the force is increasing from F1 to F2, okay, if force is increasing from F1 to your F2, then energy will be equal to how much, beta? Average of that one, F1 plus F2 divided by 2 into your extension. Very important relation. If there is an increase in the force from F1 to F2, how do you calculate the energy? Like in kinematics, you do U is equals to average of the force into your extension. Average of the force into your extension. That is half into, what is this formula I have taken right now? So half into total force. F is equals to F1 plus F2 into your extension part of relation. Is it clear for everyone? Is it clear? Sure. Next one is strain energy. I'm trying to modify this one. Strain energy. Strain energy. So what is an energy formula, beta? U is equals to your half into force into extension. Or else that is equals to your half. Force value is equals to how much, beta? Y into A divided by length L into your E square. So I can say that energy is directly proportional to E square. Okay, if Y comma area comma length are constant, I'm assuming. Is that clear? Is that clear? Okay. Next. Sure. So U is equals to half into force into extension, or it is YA by your L into your E square. Okay. U is equals to, what is the formula we got, beta? Half into your Y into A by your L into your E square. So if I rearrange this one, U is equals to your half into Y into A into E divided by L into your E. Okay. Y A into E divided by L is nothing but what, beta? Force for me. Isn't it? That is your force for me. Isn't it? YA into E divided by your L. What is force? So U is equals to your half into, this one is force into your extension. We know that one as Y is equals to stress by strain. Stress by your strain, and stress is equals to force by your area. So I can write here force is equals to your stress into your area. So U is equals to your half, Y value is, F value is equals to how much for me? Stress into your area into your extension. Okay, so what do you mean by strain? Strain is equals to your change in length divided by original length. That means E is equals to your strain into your length I can write. So that is equals to your half into stress into area of cross section is same A into this one is your strain into your L. So if I rearrange it carefully, so U is equals to your half into this one is your stress into your strain into your area into your length. Area into length will give me what beta? Volume. That means energy per your unit volume. I'll write in the next page. A into your L will be equal to your how much? A into your L is equals to your volume. That is equals to V. So I can write here the next page. Energy U is also equal to your half into stress into strain into your volume. This is also one of the very important formula in the elasticity where directly problems are being framed. That is energy divided by volume is known as U. U is known as of your energy density, small u. So energy density is equals to your half into your stress into your strain. So this is your energy density formula. Clear, beta? Is that clear? Okay. Let's see the different forms of this one, how I'm writing. Give a star mark. U is equals to your half into energy density per your unit volume is equals to your half into U is equals to your half into stress value can be written as what beta? Y into your strain into your strain. That means energy density per unit volume is equals to half into Y into your strain whole square. Okay, that means this value can also be written as very important formula beta. Energy density is also equal to your half into Y into change in length divided by original length into your whole square. Okay, now can anyone tell me what is change in length by original length beta? As alpha is equals to change in length by original length into temperature difference. So therefore, delta L by your L is also equal to alpha into delta T. So energy density is equals to half Young's modulus into alpha square into your temperature whole square. This is also one of the important formula for your energy density. Clear? Or else U by V is also equal to your. So Y value I can write in terms of this one better. So I can write even this one as of your stress whole square divided by 2 times of Young's modulus. Just rearranging this one better. Okay, strain I'm writing in terms of what? Strain I'm writing as of your stress divided by your Y. Okay, because we know this formula. Stress is by your strain is equals to your Young's modulus. So U by V is also equal to your stress whole square divided by 2 times of your Young's modulus. Clear, beta? Is it clear? Sure. One more time. But a question here, but I'm just see in the strain energy, a pure derivation, whatever derived is for your only understanding. You need to remember the formulas very carefully. The first formula is U is equals to your half into force into your extension. In terms of Young's modulus, if I'm writing, energy is also equal to your energy is also equal to your U is equals to your Y into your A into your L part deflation. Okay. Actual formula in terms of energy is this one. Energy is equals to your half into stress into strain into volume. If I take the volume down, that is known as energy density represented by letter U. Energy density is equals to half into stress into strain. So what is stress by strain beta? Stress by strain is nothing but of your Young's modulus. Okay. Now in the first case, energy density U by V is equals to half into the value of the stress. I am writing as stress can be written as what, beta? Stress is equals to Y into your strain. So that value I have substituted here. So I'm getting in the answer in terms of your strain whole square. Okay. So you know strain is nothing but what, beta? Change in length by original length. So delta L by your L. Now here I know this relation that, which one? This one. Coefficient of linear expansion. Alpha is known as what, beta? Coefficient of linear expansion. Delta L is your change in length. Small l is your original length into delta L. So delta L by your L is known as what, beta? Strain. The strain is equal to alpha. Alpha is known as what? Coefficient of linear expansion. Coefficient of your linear expansion, and delta T is your temperature difference, is known as temperature difference. So if I am writing that one, you are getting U is equal to half into Y into stress alpha square into delta T whole square. Or else U by V is also written as, now see in this formula, energy density is half into stress. Strain value can be written as, beta? Strain is equals to your stress divided by Young's modulus. Stress divided by Young's modulus. So it is the reason you are getting U by V is equals to stress square divided by your 2Y. This is your stress square. This is your stress square. Done? Sure. You need to practice this topic better. Formulas all at a time you need to remember and try to reproduce it. Next one is your right now behavior. Behavior of your Y. Just a minute. Behavior of wire under increasing loads. I already sent you one graph related to this one, beta. You need to remember that graph roughly. So when you're increasing the weight of this body, so the graph is between your x-axis and y-axis. On y-axis, you are taking stress. On an x-axis, I am taking your strain. Okay. So graph is initially something like this, beta, straight line graph. Then afterwards, there is a small bending like this. Then afterwards, again, there is a small bending. Then afterwards, something like this. Okay. So just try to remember the diagram. So somewhere at this one, we'll be getting one permanent setup. Some points you need to remember better. This is origin. This is your P. This point I'm taking it as A. This point I'm taking it as B. This point I'm taking it as C. And this point I'm taking it as of your D. The point of D is known as of your breaking stress. Is known as breaking stress. Okay. So under Hooke's law, under Hooke's law. Hooke's law means stress is directly proportional to strain from O to A. O to A is known as of your proportionality limit or proportional limit. That is known as elastic after effect. Elastic after effect will become 0 because the body will come back to the original position. O to B is known as what? Elastic limit. O to B is known as elastic limit, isn't it? O to B. Okay, O to B. That means A to B will be equal to how much? That is nothing but A to B is your elastic after effect. After effect is also 0 because up to A to B it will try to change the shape, but once you remove the external force it will come back to the original position. Then O to P from the figure is known as of your permanent set. So I can write here O2P is equals to change in length by original length. That means change in length into your L. L will be equal to how much, beta? Delta L by your L is equals to your OP, isn't it? So delta L is equal to how much for me, beta? This OP into your L is your extension. And B2C is known as of your yield point or yield range, you can say anything. So these are the some of the important terms you need to remember in this one, beta. Okay. And after the point of your C, when it comes to the point D, it will try to break it out. So that point is known as of your breaking point. That is known as of your breaking stress that I have already drawn in the diagram. Clear? Okay. O2A is your permanent limit. O2B is your elastic limit. O2P is your permanent set. And that O2P is nothing but what, beta? Change in length. And B2C is known as of your yielding range. That means from where the body is changing the shape and will not come back to the original position. Is it clear? Okay. So by this we have completed the elasticity, all the basic concepts. We'll make one more class for your numericals, so that in the next section. That means tomorrow and day after tomorrow we are having holidays 14 and 15. On 16th, we'll try to do some numericals, but I hope there will be an examination even on elasticity. That is the reason I have completed all the formula set. I've sent you some of the assignments related to this one with the solutions. Please try to do them, and also send you some of the links which you previously were have been taught. So that links also you try to go through it once. And this time we'll be having an examination on rotational mechanics and complete mechanical properties of your solids. Okay, beta? Sure. Take care. Bye.
Thank you, sir.